Okay, so today we are going to be looking at a couple equations. It's pretty easy. I think you guys are going to be fine with it. And the two equations are the equation where you can use voltage to calculate free energy, and then an equation where we can find the voltage of a non-standard cell. So this one, let's look at this, negative NFE. Delta G equals negative NFE is on your AP equation sheet, so you do not need to memorize it. What you do need to be able to do, though, is to, first off, I want you to think about spontaneity. We know that if a cell is spontaneous, what do we know about the voltage? It's positive, right? And if we put a positive number in that equation, what do we get for delta G? Negative. And does that make sense? Yeah. All right, so always check that when you're doing your work. As far as the units for everything, joules, we're going to have, delta G we're going to have in joules. N is the number of moles of electrons. What that number is the number of moles that you canceled out when you added those two equations up. So whatever that common factor of electrons when you did your half reactions is your actual number. Do it fast, get it over with. Okay. So if you have a 2 and a 5, your moles would be 10. It's whatever you canceled out. The F has to do with the charge of electrons. So most of you are in physics, and I know you know the charge of an electron. What's the charge of an electron? 1.6 times e to the negative 19th. Okay. If you take that number and you multiply it by 6.02 times 10 to the 23rd, that's the charge of 1 mole of electrons. Do we agree with that? So the number you get when you get that, and it depends. We did it last period. Depending upon how you rounded the charge of the electron, it really significantly changed this number. But that's the number we're going to use. And so that is the charge of 1 mole of electrons. So the units on this is coulombs per mole. Now, when we get to electrolysis, we're going to do some dimensional analysis problems where we're going from electron number to grams of a solid. We're going to have to do some dimensional analysis. We're going to use that as something we place in the dimensional analysis, 96,500 coulombs on top with 1 mole on the bottom, or vice versa. So this number is just the charge of 1 mole of electrons. Good? All right, so the units on this are coulombs per mole. And we know that's the unit of volt, but volt doesn't make sense if we're trying to figure out how we get joules as an answer for delta G. What are the true units on volts? Joules per coulomb. So you can see now the coulombs will cancel, the moles will cancel, and then that's where we get our joules. Okay? All right, so let's do this problem. Calculate the standard free energy change and the equilibrium constant. Oh, what are we going to do there for the following reaction? We didn't say anything about equilibrium constant yet in this unit. Yeah. So we're going to use first negative NFE to find G, and then we're going to use G to find K using negative Ratlink. Okay? So the first thing, if I want to find G, I need to first find what? Okay? Yes. In the process of finding something else, though, we will find N, but I need something E. Partially right. We need both N and E. We got to find E. That's the big thing. When we find E, we're going to do the half reactions, look up the voltages, do what we need to do, and then the N will come from that. So we're going to take, let's do magnesium first. Magnesium goes to magnesium plus 2. This is oxidation, so you're going to look on your table, you're going to find the number, and we're going to change the sign. Okay, so as reduction, it's negative. As oxidation, we're going to make it positive. And our lead 2 plus 2 electrons to straight up lead what do we get? Negative 0.13 volts. So as far as the balancing goes, this one is already balanced with 2 electrons in each equation, so we just need to add these up, which is the same as the given equation. You're going to see in a minute when we do Nernst equation how important having our balanced coefficients in this overall is going to be. So what is our overall E naught then? What? 2.226 volts. So with this being 2 decimal places, we're going to call it 2.23 volts. And that would be our E naught. Okay, so that's that one. Now our goal again was to find our free energy. So we're going to use delta G is equal to negative NFE. Delta G naught is equal to NFE naught. So delta G naught is equal to negative, what's my N? Nope, not N. 2. 2. We crossed out 2 electrons. 2 moles of electrons. It's all right, you're 0 for 2, no big deal. Faraday's constant, Rui? Yeah, 96,500 joules, coulombs, it's a charge per mole of electrons. And then what's our voltage? 2.23. And the units on this guy were joules per coulomb. So again, coulombs cancel, moles cancel. And what is our delta G of our reaction? Well, we're going to base it on the volts because that's the only thing that's not a constant. So 3 sig figs, yeah. 2 is a perfect whatever exact number, so it's not going to have sig figs. And this constant has 3 as well. Negative 430,000. Does anyone else agree? Yep. Joules. And it is negative, so it is spontaneous, and this is proving as such. Now, I'm going to go ahead and put joules per mole of reaction, because remember when I was saying when we were in thermo, I was like every delta G, every delta H, and every delta S, if you're talking about a reaction, the AP, this is very AP style, wants it reported in joules per mole. You don't have to write of reaction, but people freak out because you're like, the moles cancel. Yeah, I know, but if you have 1 mole of this reaction, that's the amount of joules that you get, okay? The only time you don't do per mole is if you're finding Q from a Calpi cup calorimeter problem. You don't throw on per mole there for no reason. And another time you don't is if it's one of those stoichiometry delta H problems where it says you combust 2 grams of this, how much heat is released? Well, it's heat per the amount of grams you combusted. It's not per mole. So those are the only two times you don't put a per mole on a thermodynamic term. Okay? All right. We're not done yet. What's the next part of this problem? We found G.
Delta G equals negative.
Yeah, now we got to find K. So delta G is equal to negative rat link, R T ln of K. Biggest mess up on this problem on the test was you guys just decided to use log base instead of natural log in your calc. So, you know, just 10 to the instead of e to the. They're not the same. All right, so we're going to plug in negative 430,000 equal to negative, which R do we use? 8.31, the energy R, not the gas R, joules per mole K, times 298 is the temperature of all our standard stuff we've been dealing with. ln of K is what we're solving for. So let's crunch some numbers. We're going to look for, are we going to get a K greater than 1 or less than 1 based on the spontaneity? Greater than 1. A negative G and a positive E means it's spontaneous in the forward direction, which means K has to be greater than 1. Yeah? They got to the 75 last period as well. I don't remember what the first part was. And that's the thing. I heard this. And then I heard, what did y'all say, 2 point what? Okay, and we're aware of this, and I saw this on the test, and we always see it on the AP. When you're dealing with these numbers, depending upon what you put in your calculator and how you round, it's going to be a little bit different. As a grader, I look at this, and I look, yeah, that's a rounding thing. And then I also, though, one thing I will do is make sure that everything is plugged in appropriately. If all those things pass, I don't care which one. But when you guys start plugging stuff in and putting down the answer without showing me, if it's off from what the rubric says, I can't give you any partial credit. So be sure to show what you plug in. All right? Okay, so now let's go to our final equation. It's actually our final equation. I think it's our final equation of the year. Because we have none with electrolysis. And then there's nothing with organics, just naming. Wow. This is our final equation, the Nernst equation. All right, here's the story about the Nernst equation. When they redesigned this AP exam, we're now on year 4, year 3 or 4, I can't remember. Anyway, they took the Nernst. Technically, they said, oh, we're taking it out of the exam, so no Nernst is needed. Yeah, they said they took it out, but then they gave problems where using the Nernst provided the easiest way to give an answer. You could come another way to get the answer. You could theoretically, logically go through all this stuff and explain. And they ended up on the rubric on the test that the first year the test was out saying, oh, we have to take the Nernst as a viable answer. So because of that, I think it's easier to explain some things. So it's not on your green sheet. I don't want you to memorize it, but what I do want you to do is put it in your calculator on the AP. So I need to compile. I'll go through, Ms. Rozier and I'll make a list of things that we think you should put in your calculator. It's not cheating, so I'm not getting you in trouble. You're allowed to use programmable calculators. You just can't use a calculator with like a keyboard, a Quartry keyboard or whatever. And you're not allowed to use your calculator on the multiple choice. And they don't clear your calculators. There's no instruction to clear your calculators. So I think we're playing the game the right way by putting things in there that we might need. So we'll get you a list at some point. But anyway, the Nernst equation, what it is finding the voltage of a cell when we've either changed the temperature or changed the concentration of one of the solutions from 1 molar to something else. This right here was the original Nernst. This is for changing the temperature. This Q comes into play when we change our concentration. I have never in the history of all the AP exams I've looked at since the 70s, I didn't look at AP exams in the 70s. I was too young at that point. But now, looking back on AP exams, they've never used this version. So this version, I just showed it to you because when you plug in 298 and you plug in the R and the F, you end up getting this number for this version. This version is the one I want you to become familiar with. This version is used when we have concentrations other than 1 molar, what the voltage becomes. So E cell is the new voltage. E naught is the voltage as if we're at standard conditions, so you do your whole half reaction atom up thing. N again is our number of moles of electrons, right? Same thing we used for negative NSE. And then the Q. The Q is the Q that you know, products over reactants. It's the same ratio as K. But why don't we call it K? Anyone have any idea? Right. What happens when a battery, it's not at equilibrium. What happens when a battery is at equilibrium? Yeah, it's dead. Remember, for a battery to work, we have a potential difference in a driving force in like one direction. As soon as we get this equilibrium thing, dead battery. So that's why they use Q here. And again, it's just product concentration over reactant concentration raised to the coefficients in the balanced equation. And that's why I'm so big about make sure you add up your equations correctly, because you're going to need your coefficients when you're solving here. All right, so let's jump into some more practice with this stuff. Calculate E cell when the ratio of those, wait, I missed one, didn't I? That one, we need this one first. All right, calculate the E for the reaction blah, blah, blah. So we're going to find E, And knowing this leads to the Nernst equation next. I'm going to go ahead and make sure my equation's all balanced, which I can tell it is, but we're still going to make sure. So zinc going to zinc plus 2 electrons. And then we have copper plus 2 electrons going to copper. So when we add these up, the 2's go away, and we have a balanced equation. So we need to find some voltages to get our E. So zinc to zinc plus 2 will be flipped. Someone find that. And I know this one's 0.34. Negative or positive? It begins as negative as reduction. We change it to positive because it's oxidation. And so our overall voltage is that exactly 1? What? Oh, because carry the 1. Yeah. 1.10 volts. All right. So that is our E. E naught is equal to 1.10 volts. Okay. Now, calculate the E cell when the ratio of these two numbers is small. That is, when zinc plus 2 is now 1 times 10 to the negative 4th. It was 1. When we calculated that E up there, it was 1. Now they're changing it. So when you see a change in concentration, immediately just say Nernst equation. I want to change this question a little bit. We're going to calculate it eventually, but more commonly, you'll get a question that says, predict if the voltage will increase, decrease, or stay the same if those concentrations are in play. So that's another way they'll ask the same question, where you don't actually have to pull out your calculator. And this is where the whole knowing the Nernst it makes life a little bit easier. So first thing, let's just plug it into Nernst and talk about it. So Nernst is E cell is equal to, what is our E naught? 1.10 volts minus 0.059. What's our N? Look it up at the equation. 2 moles times the log. All right. Product concentration. Here's what's cool about this. Both electrodes are what state of matter? Solid. Do we put solid stuff in equilibrium expressions? Nope. So we just have to do basically concentration of zinc raised to the first divided by concentration of copper raised to the first. Okay? So concentration of zinc is 1e negative 4. Concentration of copper is still 1. So before you plug in and just start solving without thinking, you might not have a calculator on this part. It might be a multiple choice question. So what would you do? Well, a couple things. You can rationalize through it, which I'll take you, but if you know your log rules, it's really simple. This is a log of a number. Do we agree that this number is less than 1? What's the log of anything less than 1? It's negative. That would be a good thing to know. So if the log of this number comes out negative, and that's a negative, what happens to the E? You got to answer the question. I'm glad he said it. He goes positive. Y'all are like throwing around positives and negatives too flagrantly. The question is, will the voltage increase, decrease, or stay the same? Answer the question. Voltage increases. And then you can show this equation. Say number less than 1 is negative. Therefore, just by showing the equation, therefore voltage increases. Now the way to do this without the Nernst equation is to look at the balanced equation. And you have to be careful, and I warned you here because students want to use the concept of shifting and Le Chat and all this stuff, but where does shifting and Le Chat belong? What kinds of equations? Equilibrium. We're not at equilibrium. So students lost points when they rationalize this just because they used the wrong terminology. So if you look, our zinc was originally at 1 molar, right? And it dropped to 1 times 10 to the negative fourth. So essentially, we took away zinc. Zinc was decreased. By removing zinc, that creates a driving force or increases the driving force of the reaction. Increasing the driving force means what for voltage? Voltage increases. Okay? Do not use the word shift. If you want to say decreasing zinc ions increases the driving force, that's cool. That's all I want you to say. Decreasing zinc plus 2 concentration increases the driving force. Therefore, voltage increases. Now, that's how to answer it if they ask you not to calculate it. And I do know they won't ask you to calculate it. I know that for a fact because they're not providing the equation, so they're not going to ask that. But they can ask the prediction thing. So, did anybody calculate it to prove it? Throw it in your calculator. The E of our cell is now that sounds about right. And it's never a huge change in voltage. It's pretty mild whenever voltage change happens. But did it increase? Yeah, it did. Okay, you guys don't have another problem. I don't know how it disappeared, but I do have another slide. You can just watch, help me out, solve it. Is everyone done with this one? Can I change the thing? Yes? Yeah, but you're not going to. They definitely won't throw that in when they're asking those kinds of questions. All right, calculate E cell of a cell which is made from silver plus 1 at 0.2 molar, cadmium, and cadmium plus 2 of 1.5 molar. So what's jumping out at you? Not 1 molar, so we know we're going to have to use the Nernst, right? What else is an issue? We need to obviously calculate E naught, but what's our deal? What are we missing? Yeah, we need the equation. We need to know what's oxidized and reduced. So what was my suggestion for that? Yeah, let's write them both as reduction and then look at those reduction potentials. Ag plus 1 electron, that's how we write that as reduction. And our cadmium is plus 2 electrons. That's how we write that. Okay, y'all look up values. 0.7991. And this one was negative. I just don't remember what it was. 0.4025. All right, so those are our voltages. As reduction potentials, which one are we going to leave reduction? Yeah, this one we're going to leave as reduction, so we're going to make this guy oxidation. So I need the balanced equation, so I'm going to go ahead and I change the sign. All right, so what is my E? .2016 volts is the number we get by adding our two half reaction potentials. And now let's do the balanced equation. Can I add these up as is? No, what do I have to do? Multiply the silver by 2, right? So I get a 2, and a 2, and a 2. So now I can add these up, and I get 2 Ag pluses. My electrons are going to go. Plus CD gives us 2 Ags plus 2 CD plus 2s. So, oh, just 1 CD, thank you. So now I have everything I need for the Nernst. So let's just make sure we know how to plug in and see if we can predict just by looking at the equation. Let's do the driving force prediction first. So, oh no, we really can't do that. This one would be hard to do it visually because one's increasing and one's decreasing, right? So it's best to set up the Nernst. And it's in a case like this, I think you kind of have to do the Nernst to figure out the prediction. So with this one, we're going to set up E. is equal to 1.2016 minus 0.059. What's my n? Noah? 2 times the log of, all right, what's the product that has concentration? Look at your balanced reaction.
Right, 1.5
1.5 is the CD, so 1.5 to the, what power? 1 divided by, silver then, it's ion, 0.2, but I've got 2 in the balanced equation, squared. All right, so let's look at this. 1.5 divided by, now we can make a prediction, 1.5 divided by that decimal is going to make something much bigger than 1, right? We all on that same page? The log of something bigger than 1 is positive. So what does this do to voltage? Okay, that's the only way you can make that prediction. There's no way you can look at the equation and do that whole shifty thing or driving force thing with this. So now, just someone plug it in and make sure our voltage decreased. That's decreased. Sounds good to me. I'm assuming it's correct. All right. That is all. You have the rest of the period, all 20 minutes, to study.